Okay, good morning. Let's begin. So first of all, I wanted to note to you that you probably saw that there is no homework posted. I don't know if you saw it or not, but the homework is not posted on Friday, and there is a reason to it. The reason to it is I'm not going to collect homework next Friday. And the main reason for it is because we only cover 2 sections and not even totally to the end, section 8.2. So you only had like 7 questions assigned, which is not a good homework assignment in my personal opinion. So for those who did it, good job. It's going to be collected in 2 weeks as part of the larger assignment this Friday. So you still need to do the questions. It's just they're not going to be collected. So, well, you did it. It's great. You need to do it. It doesn't mean you shouldn't do it. Those questions are still part of the homework. It's just it's not homework from this Friday. It's going to be posted next Friday together with whatever we cover this time. I just having just 7 questions on a homework is not enough. So you're just ahead of a game and doing great. And if there are questions about homeworks or anything, just ask. Okay, so today we will continue and finish up chapter 8. And then hopefully we're going to move on Wednesday to chapter 9, which is going to talk about relations. So just to remind you, what we are doing right now is we are talking about those recurrence relationships. We discussed that those recurrence relationships are very important because in computer science, we have a thing called recursive algorithms. And those algorithms, they work on a formula. And a lot of times we're interested to know how many operations this program does. In order to do it, we write a recurrence relation, and then we're interested to solve it, meaning we are interested to find what is the function associated with it? Like, is it in a term of exponential? How exactly is the solution is looking like? So last time we did an exercise. Actually, we did 2 of them. Both of them were for homogeneous systems. What homogeneous system means is you have a function in the form of, and let me start sharing the screen. Okay. It's a function of a form of an equal to c1 an minus 1 plus c2 an minus 2 up to ck an minus k. So those are the type of functions when you just have maybe a number and then a couple of recursive terms. However, not all systems are homogeneous. There are systems which are going to have a whole form like that. Oops. So it begins by looking at kind of like a traditional system. Constant 1 an minus 1 plus constant 2 an minus 2 plus constant k an minus k. But it also has some function of n. So the question is how you are going to solve something like this. So in order to solve something like this, you have 2 steps. The first step is you're going to solve it as a traditional homogeneous recurrence relation. So a theorem if is a particular solution of non-homogeneous come on. Why? Sorry, my pen is refusing to write. Okay, so if A and P is a non-homogeneous, is a particular solution of non-homogeneous linear recurrence. Come on, what's going on? Recurrence relation with constant coefficients. So this is the same formula I just have on top. Then every solution of the form ANP plus ANH, where ANH is a solution of the associated homogeneous recurrence relation is AN equal to C1 AN minus 1 plus C2 AN minus 2 plus CK AN minus K. So you will still need to learn both. Yes, and we are still in 8.2. So let's do an example. What do we mean by those non-homogeneous systems? So let my AN be 3AN minus 1 plus 2N. So in this case, we also need the starting condition, which is AN equal to 3. So the question is, what is the solution of this recurrence relation? Meaning, how can we write it without using the recursive term AN minus 1? Now, you can see how this one is different from the ones we did last time. Last time, we didn't have this function of N associated with it. So this is a bit different. So to solve this, we need to first solve an equal to 3an minus 1. And now, do you remember how we solve this? This is just pretty much r equal to 3 thing, correct? Because remember, we substitute r to the power n and r to the power n minus 1, and then we can get rid of r to the power n minus 1 of both sides, and we're going to get r is equal to 3 as a solution. So we know our solution for homogeneous portion of this is going to be an equal to alpha 3 to the power n. So this is what we did last time. And now this is where we need to find a particular solution. This is a solution of this function. So this is where we need to look at what is my f of n, what is the extra part I have out here. The extra part I have out here is f of n equal to 2n. And this is a polynomial of degree 1. So it has a reasonable trivial solution. So we can kind of know what the solution is going to have a form C n plus D, where C and D are some constants. Okay, give me 1 second. Somebody has unmuted. Okay, here we go. Okay, let's see. Can I scroll down a little bit? Oh, you want the theorem? Yes. So the theorem here is saying you need to look at the solution of homogeneous system, which we learned last time, and then you want to look at the solution of Fn equal to the 2n. So now this is the theorem, and now we're trying to look at the exercise to solve it. Okay, hopefully now you wrote it down. Let me go back. So now what we are going to do, we need to check if we have a solution of a form an equal to 3 an minus 1 plus 2n. Does it have cn plus d equal to 3 cn minus 1 plus d plus 2n? What have I done here? So what you do is, since it's 2n, it's polynomial of degree 1, it should have solution looking like that as another linear equation. So what you're trying to do is you're trying to plug it on both sides. So we replace an with cn plus d, and we replace an minus 1 with cn minus 1 plus d. So literally we kind of say, okay, if this one, if I'm going to treat as an and plug in original equation, what will I get? So this is what we want. And now what we want is we want to solve it. So can we solve it? Well, let's look. We have cn plus d equal to 3 cn minus c plus d plus 2n. So let's keep on going. Cn plus d equal to 3cn minus 3c plus 3d plus 2n. So what we get here is we get 2cn minus plus 2n. I'm going to put n's first, and then we have plus 2d minus 3c equal to 0. This is the equation I got. So I need a solution for this equation. The solution for it only comes to place when both terms are 0. So we kind of have two equations. So we factor n on both sides. We have 2c plus 2 multiply n plus 2d minus 3c equals 0. In order for it to equal 0, I need this portion to be 0 and this portion to be 0. So let's solve. We have two equations with two unknowns. 2c plus 2 equals 0 and 2d minus 3c equal 0. 2c equal to negative 2, c equal to negative 1 is 1, and then plug in 2d plus 3 is equal 0. I plugged negative 1 instead of c. So we have 2d equal to negative 3. D is equal to negative 3 over 2. So now I know that my particular solution is going to be of the form negative n, negative 3 over 2. How did I got it? Well, I said my particular solution is going to have a form of Cn plus d, and I found C and d, so I plugged it in. So since it was particular solution equal to Cn plus d, and we found C and d. So this is how we get it. And now, using the theorem, I know that the real solution for this equation is going to be the particular solution plus the homogeneous solution. So we need to write the particular solution, which is this. And then we need to write the homogeneous solution, which was that. Now we know A1 is equal 3, and we can find alpha. So A1 is going to be negative 1 minus 3 over 2 plus alpha multiply 3, 1, and it also must be 3. I don't need to replace the alpha. I really need a formula without alpha. So now what we have, negative 5 over 2, positive 5 over 2, 3 alpha. So now we have 3 alpha is equal 611 over 2. Alpha is equal to 11 over 6. So solution, we were looking for is an equal to negative n minus 3 over 2 plus 11 over 6 multiply 3 to the power n. So this is the answer. So yes, there is a lot of computations and a lot of things. I do want you to remember that if you have polynomials and you want to solve it, in order for polynomial to be 0, you need all the coefficients to be 0. So you must make like when you have to solve it, you are going to be solving coefficients. So you will have equations for the coefficients and you'll have to solve them. Of course, it doesn't have to be of that form. This was probably one of the simplest examples you could have gotten. Of course, your f of n might be more complicated. If your f of n is going to be a form of, I don't know, 5 to the power n, for example, then in this case, you will be looking at solution of the form. So particular solution in this case is going to be constant multiply 5n. Does it make sense? And if you're going to have f of n equal, I don't know, 5n squared plus 3n minus 2, your particular solution is going to be of a form a. Well, I already used a. I do not want a. Let's do b n squared plus cn plus d is going to be your guess for the solution. So they're always going to have the similar form to the function with some constants nearby. Does that make sense? This is how you get, those are how you guess particular solution. Okay? So I highly suggest reading carefully 8.2. It has many more examples. Some of them are going to be more complicated than something I can include, for example, on the test. However, questions similar to what I did last time in class for you are pretty straightforward compared to what you can get. So you really need to learn how to do the homogeneous systems. For sure, you need some understanding on how to do non-homogeneous systems too. Again, play with it, look at it, do a couple of exercises. Okay, so I already gave you the solution of, not solution, the assignment for the homework from 8.2. I also want you to look at special case. I probably should kind of say it. Sometimes you are going to have roots which are going to repeat more than once. And in this case, where do I have an example like that? The solution is going to look a bit different. This is going to be on page let's see. Yeah, this is going to be on page 542 of your textbook. If it has, there's going to be a theorem for two distinct rules, and then there is going to be a theorem for non-distinct cases. I promise you on the test, if you're going to have a question similar to it, it's going to be distinct roots just because, you know, it makes things a tiny bit less complex. Now, those of you who would ever go to differential equations, you're going to see a lot of similar things. This is literally like differential equation is all built on those breaks into homogeneous system and non-homogeneous system and solving separately homogeneous system and linear system. So this is really a piece of like a bit connected to differential equation with the difference there is no derivatives involved. Okay. And we are going to move on and we are going to talk a little bit about divide and conquer algorithms and recurrences. So So first of all, the idea of divide and conquer algorithms in computer science is, and not only in computer science, is to divide into sub-problems similar to original problem of smaller size, solve recursively subproblems, and then conquer, and this is what was bothering me. I did misspell it, conquer, and it still looks wrong to get the answer. And here is an example for you. I have, you can think about it as a sequence or set of elements, but they're going to be ordered. So in computer science, we call it arrays. And I have numbers here, 1, 5. Actually, this one is too huge. Let's do something smaller. So 1, 5. $17, $22, $33, $41, $52, $53, $60. Something like that. And assume I ask you something like, can you find me? And you can think about it as an apartment building. So it has indexes out here. So every number lives in an apartment, number 0 through 8. And I'm going to ask you a question of, do I have a person or like a number 35 in it? And if so, where is it located? Okay. So the traditional way of thinking about it is, okay, let's see, who lives in apartment 0? 1. Is it 35? No, so I should keep going. Let's go to the next apartment. Next apartment is 1. Do I have 35 in it? No, I don't. Keep going. Then I can check 17, 22, 33, 41, 52, 53, 60, and I can see that there is no 35 in there. So I can say, okay, too bad, 35 is not there. Now, what if I'm looking for 53? I can do something similar. I can say, is it an apartment 0? No. Is it an apartment 1? No. 2, 3, 4, 5, and you're going to find it later and say my 52 is located at apartment. At what apartment 52 is located? Apartment 6, correct? Because there is a number 6 on top of it. However, how long does it take me to check every single apartment sequentially as I start from this apartment 0 and so on? It takes me as many as elements I have out there. However, if you are looking very closely at my numbers who live in the apartment, there is one property I'm not using. What property I'm not using? Is, yes, my numbers are ordered. So first of all, when I was looking at 35, after I looked at 41, did I have to keep on going? No, correct? So I can make my life a little bit easier and say I always stop when I see number larger than what I need, correct? But it's not too huge of an way of doing it. There is a better way. And this better way is called binary search. And I'm sure many of you heard about it before, but it's called binary search that uses that specific divide and conquer algorithm. So binary search tells me this. It says, okay, find a midpoint. In this case, my midpoint is what apartment is a mid apartment? 4, correct? So we are going to say, okay, I'm in apartment 4. What I'm going to do is I'm going to say, find the mid apartment and check who is there. So assume I'm looking for 52. I'm going to say, okay, compare 52 and 33. So what is larger, 52 or 33? Well, hopefully we know 52. So what does it mean? My number 52, if it is in there, is it going to be located on the left side or on the right side? It must be on the right, correct? It cannot be on the left, always right. So that means I literally can kind of illuminate this thing. It's not here, correct? I do not need to check here at all. So now what I can do is I can say, okay, so Zeus I already checked and I don't already checked and I don't need to check it anymore. Now I have from 5 to 8. What is the midpoint between 5 and 8? Well, depending if you round down or up, it's either 6 or 7. Let's round down, so 6 in this case. So what we're going to do is we're going to look at the 6, and here, luckily, I already found 52, so I can return it. However, if I would have been looking for 60, for example, I would have to continue, correct? And there is also an option of me like not getting the number. So at some point, it's going to be with my indexes. I do not have any elements to check. It's just not there anymore, correct? So you can write an algorithm on how to do it. So this type of thing is called divide and conquer, because what I do is I divide my problem into sub-problem. I'm saying, okay, I'm looking in the middle and I'm literally getting rid of a half, and I need to repeat the same process, but now for my right half. So pretty much I run an exact same algorithm. I do exact same thing to the right side, correct? And my solution is my original solution. So the question is, how exactly is it connected to chapter 8 and the recurrence relationship we were just doing? Well, the fact is we now have discussed how many steps it's going to take me to run such an algorithm. So when I did it starting from apartment 0, 1, 2, 3, 4, 5, my running time would have been just n, correct? So as many as n apartments. I will need to do the n operation before I can conclude it's not there, correct? Or there at most, yes, but it's going to be around that, correct? Now, how many operations the binary search is going to take? Well, since I'm using divide and conquer, I cannot tell you number, right? But what I can tell you is I can write, this is sequential. So start with 0, go till n minus 1. And then how will a formula look for, well, actually, I can do something like that for the formula. You can do it with +1 or you can do it with +2. I'm doing it with +2 because I need one operation in order to calculate the midpoint and one operation to compare. So this is why +2. But generally, it is going to be a formula like this. And this formula is recurrence formula. And actually, this formula is going to give you O of log n base 2 time. But this is how generally those things are connected. So there are many algorithms, and I'm not going to show you those algorithms. However, there are many divide and conquer algorithms, including merge sort. Somebody mentioned sort here before, which are divide and not conquer, and we're interested to know how to bound the time. So generally, if you have a formula of a form Rtn minus 1 plus Gn n bigger than 0, and then there is some number for T0 when n is equal to 0, my solution for such formula is going to be Rn to the power T0 plus summation of R to the power I G n minus I goes from 0 to n minus 1. An example is going to be solving Tn equal to 4 Tn minus 1 plus 2n. T0 is equal to 6. Now, what you can do is you can solve it, and if you solve it, you're going to actually get what the solution is going to be 7 multiplied 4n minus 2n, and then you can literally prove that those two are same. Proof using induction. I'm not going to waste your time in class on it. It's kind of a lot of questions here. In this case, your R is 2 square. Well, this is, sorry, your R is 4. So what you look, it's a good question. How do I figure out what is my R and what is my G? So in this case, the first thing, this is your R, and this is your, oops, Gn. I do have, and I'll need to find it, but I do have already a video where I solve this problem, including the induction proof. I'm going to post it for you to watch. Now, we already did a lot of like proofs like this when you have to prove those two are connected to each other. Now, I do not need you to memorize all of it. I just want you to see how in a real life those things are used. I made you do a lot of those sequencing and things. What I'm doing today is hopefully I'm giving you a real life example on how those things use. Merge sort, which you, like, I'm sure many of you heard about it before, and if you didn't, you're going to hear about it in data structures and probably CS1 and then algorithm analysis, and you're going to do it again. But merge sort is going to be actually Tn equal to 2, not merge sort. Yes, merge sort is going to be 2Tn over 2 plus 2 formula. And then those algorithms are algorithms of type, when I can say over here, the very first algorithm, I can also write it as a recurrence by saying check the 0, check this element, and then recursively check for it over here. That makes sense? So those are going to have those type of formulas. Now, one more special formula for you. This one is very common for computer science algorithms when you halve things. So it's going to be 1 when n equal to 1, and then it's going to have a formula like that. For example, merge sort will have similar formula. And actually, I'm already going to give you away the thing. The running time of it is n log n. The question is, how do we get it? And here is what I'm going to show you. I'm going to draw a tree for you. So let's see. At the beginning, I start with n elements and they're all combined into the one. Then what we need to do is we need to halve things. Do you agree? So I'm going to have half here and half here. And I'm going to have n over 2 elements in each half. So you can think about it. This is my I equal to 0, and I have one kind of problem to solve. Then I have I equal to 1, and I have 2 problems I need to solve. Then I'm going to solve each of the halves separately in the recursive way, correct? So as I do it, I will need to halve each of the halves. So this is going to be like n over 4 for each of those problems when my I is equal to, and I have 4 problems out here. Now we are going to repeat this division process. We will have n over 8, I equal to 3, and 8 things here. I want you to look at something interesting. This is 2 to the power 0. This is 2 to the power 1. This is 2 squared, and this is 2 cubed. The question is, when do you think I'm going to run out of elements? I cannot divide forever, correct? I started with n elements. At some point, I'm going to divide that to fractions, correct? I cannot divide one element into 2 halves, correct? At some point, I'm going to have here just one element, correct? And all of the sub problems, I'll just have one element. The question is, where do I reach it? What is going to be my I in this squares? Well, it's probably kind of intuitive when you think it might be n, but it's really not. Because do you see how my number of elements changes as a progression of 2? So pretty much I'm going to stop when n is equal to 2 to the power of I. So when I reach correct amount of elements. But if n, let me go down. Oops. But if n is equal to 2 to the power of I, let's apply log base 2 on both sides. This is the same as I log 2, and this is just 1, correct? So I'm going to stop when this thing is log base 2 of n. And then how many operations do I do on each of those? And you're going to see here that I always do n operations. So this is how we get n of log n time for this formula. Okay. So this is why people say like merge sort, for example, is n log 2. Okay, so this was section 8.3, and you're going to do question 2 and 7. And trust me, they're going to be easier than most of the things I showed you, but it's supposed to give you a flavor of a real applications. Okay, now we are into section 8.5. We are not going to cover endpoint, and it talks about inclusion, exclusion. So recall a problem which you all supposed to know how to solve. How many numbers are divisible by 3 and 5? And 5 numbers from 1 to 20. Do you know how to solve this one? We did it. You just passed the test on it. So tell me how we are going to solve it. Step 1 is how many divisible by 3. What is my step 2? Yeah, inclusive, exclusive, it's not an idea right now. How many divisible by 5? And now I add and I'm done. Okay, why no? What else should I do? Correct. Some are divisible by 3 and 5. So we double counted share ones. So we need to subtract divisible by 15, correct? So this thing has a name, and the name for it is inclusion, exclusion. If you have two sets, and I want to know how many elements are in A and B, I'll need to include A plus B and subtract what I double counted. This is called inclusion and exclusion. Next time, I'm going to show you principle of inclusion and exclusion for 3, because right now it was for 2 sets. We're going to learn it for 3 sets and generalize for n sets. And this is just a concept which you're already familiar with. And pretty much there is not much to do with it. There are problems with it. And you always need to remember, when you do this counting, you need to add and subtract. Add and subtract. And we will talk about it more next time. Have a good day.